Okay, so let me share the screen now. Okay, so today we will be doing series and parallel circuits, and series and parallel circuits are actually as we are doing them in the lectures too. So there are two things that are involved: series resistance, parallel resistance. Then there is a current division, voltage division. So that helps us to know the current around the circuit and among the components. Till now, we just have resistors as a component. So I think that will help us to understand that. This lab is not simulation-wise hectic. It's very easy to do, but this lab is about understanding the concepts, what we are doing. Okay, so let's start it. So first, I'm trying to do series resistance, and I think we did in the class too, so we are all familiar with that. So series resistance, if there are three resistances in series, we can calculate it like that. RT is equals to R1 plus R2 plus R3. If they all are equal resistances, then it can be replaced as 3R or NR, and the total resistance can be determined using the Ohm's law. That's voltage, this voltage divided by the current that is flowing in it. So that's about the series resistance. Then when we are talking about series resistance, there are the voltage drops across these resistances, right? So let's say this is V1, V2, and V3. And due to these voltage drops, we can find out, based on our voltage divider rule, how to find the voltage across R1, R2, or R3 by applying voltage divided rule. Okay, so here you can see that if we have to find V1, we can just do R1 divide by total resistance, multiply your voltage. So that's how we can find voltages across each element. The other thing is that we need to find power dissipation, right? So power dissipation across resistors can be found if there is a single current flowing. You just need to know the current and you can multiply with the resistance. Or if there is voltage that is known to you, you can just do V square over R. So that's how you find power dissipation across the resistors. Okay, so what you need to do in this lab, you can start with your basic circuit. That was your basic circuit. I just did not have the label nets, but you were having the label nets as well. Now what you need to do, calculate the output voltage. So this was the output voltage in the previous circuit. And with the above formula was like the voltage divider formula, and verify your simulated results for V out. Like I just put it here, like it could be 1K divided by 1K plus 1K into V in, because this was your V out. Then what you need to do, replace 1 kilo ohm resistor R2 with 1 mega ohm resistor and calculate V out again, okay? And record the simulated value for the current, voltage, and power dissipation. So what you need to do, you calculate, you put 1 mega ohm here, calculate value using the voltage divider rule, and find the simulated value and current and power dissipation. So let me show how we can find the current and power dissipation. The other thing is you need to replace 1 kilo ohms with 1 ohms and see how the current, voltage, and power dissipation changes. So you can see that if I change this resistor to be very large resistance, let's say 1 mega ohm, what do you think should happen to the current, voltage, and power dissipation? So if I want to measure the power dissipation across R2, to which value it should depend? I mean, you cannot just say any number, but you know the power dissipation formula. So power dissipation should be large, small, what do you think?
Large.
Large.
Because it's directly proportional to R, right?
Yeah.
Yeah. But what do you think will happen to your current if this resistance is very large?
The current's going to decrease by a lot.
Yes. So maybe power decrease too. So let's just check, okay? Let me share my LTSpice screen, and then we see. Okay. There is one more thing I wanted to tell. Can you see my screen here?
Yes.
Okay. So some of us, I think myself also was having problem in having the black screen of simulation. So you can just go into the waveforms, click in the color scheme, and I just make my background of waveform as 255, 255, 255, which is the RGB value of white color. And so then it can, my waveforms will appear on the white screen. You will see that. So I just need to change this. Then kilo ohms. Okay, I need to cut this. Okay. You guys may be wondering what it is. You will know that, don't worry, okay? And okay, so for Mac users, what I figured out is that everything is available by right click. So if you right click there, there is view, there is edit, there is draft, there is draw waveform, everything. So if you want to do the spice directive, you can go in the spice directive. If you want to go, what you should say, what was hard to find before, you can just right click it. I think delete, you can just right click in and do that. So it makes it really easy for them to find out the things. Okay, so what I'm trying to say is let's change it to 1 meg. Okay, and my input voltage was 12 volts or 9 volts before.
Should we be building this on our screen too?
No, it's okay. I
Okay.
mean, you were having before, right? I'm just showing what's it's gonna happen. So if you see, you can see that your V out is very large, right? Like previously it was 4.5 volts when you were having equal resistances, right? Do you understand what I'm saying?
Yes.
Now, because this resistance is very large, like R2 is very large, you are having most of the voltage drop across R2, right? Now you can see that your device currents are also reduced by a huge amount, what you should say, right? So because, why it's happening? Because you have 9 volts divided by, now your resistance is increased by at least 10 raised to power 3, right? So that's why your current is reduced. So it's like you have a pipe, and when you squeeze the pipe really hard, so it's very hard for the water to flow. So it's like you increase the resistance. So that's what's happening. That your current is decreased by increasing the resistance too much. Now we talked about, okay, 9 volts here, and 8.99 volts here. But what I want to see is, okay, let me do another thing. Okay, so that's what I was talking about, that I wanted to my waveform like that. So this is V in. Should make it a little bit bigger. Okay, so this is my V in. This is my V out, which is very large. And this is my current. And if I do Alt and click it, it will show me the power, okay? Power dissipation. So you guys can see that I can now see power dissipation as well across V in, that is minus 80.919 microwatt. Why do you think that this power dissipation is in minus value, showing me the minus value? Why do you think? What do you think? Okay, I should create.
Because Vn is the source of the power, and so it's going to get used up.
Yes. So it's showing me the positive, it's showing me the negative value because it's supplying the power, right? So if you want to know power, you can see, can you see the bottom bar in my window?
Yeah.
It's also showing you the dissipation, right? So it's here, the dissipation is minus 80.9. Similarly, you can get the dissipation here and here too. What we anticipated that as we increase the voltage, our power should increase, right? Let's see. I think it's, okay. So you can see the power dissipation across R2 is 80.8 microwatt, right? But power dissipation across R1 is 80.8 nanowatts. What is more, nano or micro?
Micro?
Micro is higher, right? Because it's
Yeah,
10 to the power minus 6 and nano is 10 to the power minus 9, right? Why power dissipation is lesser across R1?
Because the resistance is lower?
Yes, because the resistance is lower. That's why, right? That's why you are seeing more power dissipation across R2. So that's what we want to see in this lab, that what is happening when we are increasing the power. Okay. So that's what you were doing. Replace 1 kilo ohm with 1 mega ohm, and then replace 1 kilo ohm with 1 ohm to see what really is the difference in your current voltages and power dissipation, right? So you can show it with your calculations and compare it with your simulations. Okay, so what the exercise is saying, by simply noting the relative magnitude of resistor R1 and R2, how would you expect the applied voltage to divide between the resistor elements? Exactly, it's the same question, but we really want to understand what is happening if you increase one of the resistance, what is happening to VR1, which is V1 in the previous case scenario. Here it's VR1, and don't confuse this V1 with this V1, which we have put. You can just put it E as well, okay? So what I'm trying to say is that you need to really write it in words that what do you think that R1 and R2 values have an impact or V out, okay? Then you have to design the circuit that produces the output voltage 2 volts with 12 volt power supply. Now you can design the circuit as well, because what you need to do, you need to take this, what you should say, formula. You need to choose these resistor value. You know V out and V in. If you just pick one resistor value, something, you can find out other resistor value. But the point here is that you need to use standard values. So standard values are these. So these values are those which are available in the market, okay? So how these values work, if you see this 10 number, so it means that you have 10 ohms, you have 100 ohms, you have 1K, you have 10K, 100K, something like that. So these values are available for all the powers. So you can choose one of the resistors from there, and you need to find out what will be R2 to give you 2 volts when you will have 12 volt supply. Am I clear?
Yeah.
Okay, so let's move forward. Okay, so now we are talking about parallel resistances. So what is parallel resistance? I think most of you know now, but I just want to repeat it. Parallel resistance and current division, that's what we are talking about. So what is parallel resistance? In parallel resistance, you have resistances that attach in parallel with the supply. And instead of the voltage division, there is the current division, because here in the node, all the voltages are same, but current is dividing here. So what we are doing is, we know that the total resistance that we calculate here will be RT. And if we know that, it means that our equivalent circuit, if we draw, will be this will be our RT. And this RT will be the parallel combination of these all resistors, right? So it depends how many resistors you have. Let's say here it's saying that you have 2 resistors, then this RT will be equal to this R1 into R2, R1 plus R2. So that's how you calculate your total resistance, and then you can find your I here, because you know your E, and you can find your I here, total current that is flowing here, this one, this I, right? Understand?
Yeah.
Okay, so how you're gonna find these I's, right? So we can find these I's like I1, let's say, is E over R1, right? Similarly, I2 will be like that. But, okay, so how you will find it through simulation? Through simulation, if you have 2 resistances in parallel, you will put your current probe here. Here you will have your current probe. And it should give you total current, right? Current probe, and it should give you I. That is total I or IS, whatever it's saying. But it will be the simulated value, right? So this will be, so whatever you find through current probe will be your simulated value. So this will be I sim, whatever you said. So how you can find your I1 sim if you want to find it? What do you think? Sim means the simulated value of I1. How do you find it?
Put the current probe on R1.
Yes, put the current probe here. You will find I1 sim, right? Similarly for other resistors. So the thing we are saying is that I1 we can find, these are the calculated value, and the other was the simulated value. One more thing I wanted to show, just a minute. So here I referred some figure 6.1, right? This figure 6.1 means that I referred it to your lab manual book. So it's figure 6.1 in that book, in the lab manual. So we are not following the whole manual as it is, but we are picking some things. So if you can go in the lab manual, you can also see the theory behind that.
What page is it?
So page number is number 70. Okay, so so we are clear how to find I-sim and I1 sim and how to calculate these values, right?
Yeah.
Okay, let's go move forward. So that's what you have to do. You have to construct the circuit in figure 6.4 that is given in the book, and I also showed it here. So those who don't have the book, I actually try to what you should say, replicate the tables as well, which I am referring to, because I will upload another document, like the Word document, in which I will be showing that these tables should look like that, so they don't have the problem for now if they don't have the book. Okay, so construct the circuit. This is the circuit. Let me check the pointer. So this is the circuit you need to construct. And these are the values you need to put. You can find your, you know, the supply voltage, that is E. You can find your I here. This I is nothing but just a current probe if you put it across E. This, why it is showing it here, because when we measure it in real world, we put multimeter, we break the circuit and put multimeter in the way. That's why it's like that. For simulation purposes, current probe on E can serve the purpose. Okay, so don't worry what is this EI here. Then calculate the total resistance using equation 6. Equation 6 is this one. This equation 6 I'm referring to, and record in table 6.1. So let me check what is table 6.1. Okay, so in table 6.1, you have total resistance, you have R ohm meter. This R ohm meter you can cross because you don't have ohm meter to do that. So percentage difference here is the simulated value and the calculated value. If you don't have, let's say, the like no difference is there, so you can just put 0, okay? Then RT equation 6.2. So you have two equations to find your RT, which is fine, and then R using Ohm law. So this is the RT using Ohm law, this is the RT using equation 6.2, and this is the RT using 6. So it's that's what they ask you to record in 6.1. What is the difference between calculated value and simulated value? Simulated values are the values that you get by putting the current probe on your elements. Okay? Am I clear?
Yeah.
No?
Yep. Yeah, you are.
Okay, so that's what we want, okay? Okay, so the exercise says that normally the theory states that the total resistance of parallel network will always be less than the smallest resistor. What it means that you have 1.2K, 2.2K. The equivalent resistance will be less than 1.2K. So you need to prove that whether is it right or wrong. What will happen if you put 3.3K resistance here? But it means that if you have to put 3.3K resistance here, what will be your equivalent resistance, how it affect your currents, and things like that. That's you need to show. And how does the total resistance compare to the magnitude of the smallest? So is it still the smallest resistance, the equivalent resistance, and has the addition of 3.3 kilo ohm resistor reduced the total resistance below the previous part of the experiment? What is the difference between the equivalent resistance that you're getting here and the equivalent resistance you were getting in the procedure? Will the total resistance of parallel network always decrease in magnitude with the connection of additional parallel elements? What do you think? Okay, so that's what you need to answer in that question. Okay, so now we are heading towards resistance tolerance. So in real world, have you guys picked up your kits?
Yes.
Yeah.
Okay, that's good. Because today is the last day, right?
Yep.
Okay, so in real world, all the resistances are not exact the values that we are given them. They change because of room temperature, because of all the stuff that's going on around us, okay? So that's why in the practical scenario, they have defined the tolerance. So what is resistance tolerance? Resistance tolerance is the value that they have defined that the resistance value can be changed that much. So let's say if they have defined that your resistance tolerance is plus minus 1%, it means that if you have the 1 kilo ohm resistance, the resistance can vary between 1010 ohms to 990 ohms, which means the worst case value of the resistance is the original resistance value plus the tolerance value, like the 1% value. You know, 1% of 1K is 10 ohms, right? So when you add 10 ohms in it, it will be 10 ohms. When you subtract it, 990 ohms. So what I want you guys to do is start with the basic circuit, that is lab 1, change worst case values of resistors. So whatever resistor values you have in the first lab circuit, change their values to their worst case values. Let's say you change them to 10, 10, 10, 10. So this is the one end of the worst case value. The other end of the worst case value, change both the resistors to 990, 990. Then you change to 990 and 1010. So what is the difference of voltage you will observe by changing the tolerance, right? So here the calculated value should be the value which you get from 1K ohms, not with the value you get because the change in tolerance. Like let's say you calculated value that is actually with 1K is 2 volts, then simulated value after changing the worst case value should be different, right? So your percentage difference will be changed, right? So that's what you need to do here. Discuss the effect of nominal versus actual values from each step. So you need to know how much percentage difference it creates if the tolerance acts in the worst case scenario. Got it?
Okay.
I know it's too much information, but it's not difficult. I mean, all things are laying, we have mentioned them. So if you follow step by step, it will be easy. Okay. So now what you have to do here. Okay, so one thing is tolerance, that is resistors changing their values. The other things are power rating. So what is power rating? We know that these resistors are passive devices, right? So they, what you should say, dissipate energy across them, but they cannot dissipate infinite energy across them. There is some rating. So they have defined that this resistor cannot work beyond this much power rating, okay? So that's what we need to know about resistors, that how much rating is there for the resistors. So what we will do here is, we will construct this circuit that is 10.1. And in this circuit, you see that we are defined 1/2 watt and 1/4 watt. So 1/2 watt is the rating that is given us for the resistor. So 1/4 watt is another rating that is given us for the resistor. So 1/4 is actually 0.25 watt, right? Which is equals to 250 milliwatt. So what it says, calculate the maximum voltage of V load for which the power to R2 is equal to 250 milliwatt. So by given this formula, you will calculate the, what you should say, voltage that you can apply keeping this resistor under its maximum power rating. So its maximum power rating is 250 milliwatt, right? So this is the thing you are doing here. So you are trying to find what is the voltage here that you can apply by keeping this resistor under its power rating. So its power rating is 250 milliwatt. Into R is equal to V. So that's what you will find and record it in 10.1, table 10.1. So for summation purpose, if you want to, recreate your tables, it's fine. Or even if you want to fill it in and take the picture and then attach it, it's also fine. It's up to you. But I think if there is a little change in table, we can just recreate it. Okay, let me see, 10.1. Okay, so 10.1 is nothing, but you just have to add the source and the V load in it, okay? So what is the V load that you are getting? That you're getting. Let's say, I think I was getting 9 volts here. So it means that I can apply 9 volts across this resistor only to keep this under its rating. If we apply more than that, this resistor will be under constant pressure of working beyond its rating, right? So what is the required source voltage to produce V load at output? We can determine that as well because we are given the resistor values and we can just find out the output voltage. Calculate the power dissipation across the resistors. What percentage was the power of R1's rated power? Fill the table 10.2. So how you will find the percentage power is this. So let's say a resistance, okay. Okay. Well, let's say the resistance is work, or the power dissipation that you have calculated is 70 watts, right? 70 milliwatts. 70 watts is too much. 70 milliwatts. So, and you need to calculate that the percentage of how much percentage of rated power it's working. So percentage is 70 milliwatt divided by 250 milliwatt into 100. But same, if I have to do same thing for R1, right? I was just supposing that this is R2. But let's say if I have to do the same thing for R1, what I have to change here? Let's say 70 milliwatt is the dissipation across R1, right? So what is the rated power of R1? What is the rated power of R2? What is the power rating of R2? That is given.
0.25 watts.
0.25 watts, right? Which is equals to 250 milliwatts, right? So 0.25 watts from where we know? where it is given in the circuit.
It's written under resistor 2.
Yes, so this is the rating that is given, right? So what is the rating of R1?
Half of what?
Half watt, right? So it means that if we calculate that the rating is half watt, which is 500 milliwatt. Right? So this should be, let's say the dissipation across here, the R1 is 70 milliwatt divided by its rated power, that is 500 milliwatt, is I think equal to, I'm not sure, but I think it's equal to 28%. So it means that it's 28% of rated power, right? What percentage was the power of R1's rated power it has used? It has used 28% of its rated power. Understand what I'm saying?
Yeah.
Yeah, so that's what we are trying to do here. Okay. Then use DC voltage sweep. Sweep means that you need to sweep it from, change the values from 0 to 25 volts and see how much dissipation we are getting across both the resistors, right? And what is the V load that is you are getting? V load is this voltage. Then you need to calculate the percentage powers of rated powers of both the resistors. The other thing is that if you, let's say you think 25 values are too much, you can take every alternate value. So it will make them half of them, right? We just want to know the trend that you are getting in the table for multiple values for the V load and power dissipation. Then if V source is 25 volt, what will be for the highest value, what will be the power dissipation across R2? Will it be safe to drive R2 at that voltage? How we know that it is safe to drive that? If it exceeds its 100% of rating, right? Then it's not safe to drive it. So that's what you know, that if it is more than 100% percentage of the rated power it is using, then it's not safe. Now draw graph between power dissipation and voltage across R2. So now you have 25 or let's say 12 values, right? Across for voltage across R2. So, and you know the power dissipation. So you just need to draw the graph by putting power dissipation in the y-axis and voltage across 2 at the x-axis. Okay? Am I clear?
Yeah.
Okay. Okay. So now it's very practical scenario that we are talking about. Is the, okay, it's, I think I annotated before. Okay, so it's the battery model. So what is battery model? Normally, the voltage source that we use is the ideal voltage source because we don't think that it has any internal resistance. So that is called the ideal battery. Like if battery has no internal resistance, it is an ideal voltage source, meaning the battery terminals and thus the voltage across the VR will always be the same regardless of how low the resistance is. So, but in the real world, what happens is that if you have, like what we think normally, that if there is a voltage source and we reduce the resistance here, it will keep on increasing the current, right? So, but it's not happen like that. It's not keep on increasing the current because it has its own resistance, internal resistance attached to its voltage source. So we don't see, but our battery has its own internal resistance. So what is happening here is, I think we talked about that in class 2 today, that what is happening that if a real battery has internal resistance RB, which means any increase in current due to current drawn by the voltmeter will cause a voltage drop. Okay, so this thing we need to understand. So let's say we have applied this, we want to measure voltage across this R. And now we have connected voltmeter across that, right? Let's say this what you should say, the resistance is 5 ohms, and this is 1 mega ohms. So this will give you approximately resistance at approximately 5 ohm, and it will be approximately what you should say accurate or precise voltage. Excuse me. But if we reduce this resistance to 1 k ohms, right, the parallel resistance of the voltmeter, then it significantly draws the current here too. I think I showed you before that if you increase the resistance too much, like 1 mega ohm, it normally doesn't draw current here, right? But if you reduce this resistance, this part also draws the current. Understand what I'm saying?
Yeah.
Others?
Yeah.
Okay. So we don't want that the circuit the measuring device that we have put in the circuit should not draw the current. It should just do the purpose what we put it that it should serve the purpose that we want it to use, right? So the voltmeter should not have a lower resistance or approximately equal resistance to the resistor across which we are measuring the voltage. So its resistance should be very large. That's why we are trying to understand that how it works. So this internal resistance we can calculate also practically, that we will do when we will use the kits, okay? So another way of looking at it as, so this is your ideal battery scenario. So this is your E true, which is your practical E, which is equal to E minus IR int, because your original E minus your drop across internal resistance, right? So as this internal resistance will have a drop, that's why your E true is not equal to E, okay? So that's why we need to consider that. And I have put some link here. That is the YouTube link, and that talks about the practical scenario that you will be having if you think that it's an ideal voltage source. Similarly, again, the same thing I'm talking about, but it's just a different way of looking at it, is that if you have 10 volts here and you are thinking that your E load is 10 volts, but in an actual scenario, it's not like that. It's actually 8.3 amperes current it's flowing, and the original E load is 8.33 volts, which is lesser than original value. And it makes sense, I think, when we say anything in the practical scenario, it's not actually the thing, because we need to like tackle the real world scenarios, okay? So what we need to do here? Okay, so as we have done many things in this lab, we know power rating, we know tolerance, we know real battery scenario. So we will try to apply all of them here, okay? So what we will do, we have a voltage source that divides a 12 volt battery in a 2 volt output that you have done before maybe. And in LTSpice, a battery can be found in this miscellaneous section of the component, okay? So let me try to do that. So I actually already got the battery, but I just need to show you how I got it. So it's okay if you do previous parts using voltage source, or if you want to do it with the battery, it's okay, but just put your internal resistance is equals to 0, because we are thinking that it's a ideal scenario, okay? So I just put the battery here, and I should get it here like that. And if you just double click it, so you will get the series resistance and DC value you can put. So it can change its series resistance as well.
The series resistance is going to be our internal resistance of the battery?
Yes, yes, yes.
Okay.
Yes. Yeah. Okay, so.
Oh, wait, Professor, then one quick question. So, like, then every battery we actually get from, like, whenever we buy, like, a 9-volt battery, is it actually closer to, like, a 9.5, but it actually has internal resistance that lowers the voltage? Or something like that?
Yes.
Oh.
It's actually lower than its rating, what it shows.
Oh, okay.
Yeah. You will, I mean, the link I have shared, they are talking about something about car batteries too. So you can look at it too.
Okay, thank you.
Okay, so be sure to use standard value resistances. We are thinking that they are 1/8 watt powers. By right clicking on the battery symbol, you can set the battery voltage. That's what you can do. Start with 12 volts and 0 ohm resistors. Okay, so you can see that I have a certain voltage divider here that can produce 2 volts. So in the previous question, in which I am asking you to design the voltage divider, you can use some other resistances that are given in the standard values, okay? So that will help you to learn how you can design voltage divider, okay? So modify the part 1 as follows and rerun the simulation. Change the internal resistance. Now you start changing the internal resistance. Using 5 values, starting from 1 ohms and ending at 10K ohms. And then record your results, right? Then you will change, then you will see what your V out will be, how it's changing due to the internal resistance. Set the battery internal resistance to 0 ohms again, and go back to your nominal resistance value. Add a 1 kilo ohm resistor between the output of your voltage divider and ground. So that's what actually you need to do. Set it again 0 and add the 1 kilo ohm resistor here, okay? Compare the theoretical voltage, current, and power for this circuit with the simulated result. So you need to, again, calculate the voltage, current, and power and the effect of the 1 kilo ohm load that is having on your circuit. Be sure to record the results of all simulation in your spreadsheet. Your voltage divider with the 1 kilo ohm should look like this, right? So that's what we are trying to model, that it's actually the voltage source that you are, the voltmeter that you're having here that can affect your circuit. So that's, you should be very careful about. Okay, so this is the final exercise in which you need to discuss the effect of changing the battery series resistors. What do you think series resistor model has an effect on the output voltage? Discuss the effect of load resistor on your circuit. What will be the its effect on Vout if we change or increase RL to 1 mega ohms? What are the standard resistor value? And how does it tell you that you cannot use any resistor value that you want to build your circuit, because there are some discrete values that exist. So that's about it. There is one more circuit but I don't want to do this right now. I want you to understand what's happening here, and then we will move forward. So you can start doing it, and I'm here. Okay? Sounds good?
So will we go over that last circuit at the end of the lab?
No, we will go next time.
So it'll be the beginning of the next lab.
Yeah.
Okay.
Okay. And
So-
I want to give, okay, sorry, go ahead.
Sorry, I just wanted to check. So is this going to be like last week where we do the lab now in case we have any questions, but it's still due at the beginning of next week?
Yeah, that's what I want to tell, that I want this lab report to be submitted not next week, but after the next week, okay?
Okay, thank you.
And because there are circuits that I'll be talking about, and I think I will not be having one of the lab on Tuesday, so this lab we will be having, so we can talk about these stuff. So what we are doing, we will do another circuit, and then we will start our lab in which we will introduce our equipment that you are getting in the kit. Okay?
Okay, thank you.
Thank you. So I will stop the recording now. And then you can ask any question if you want.